Hi everyone, I'm Eric Tao. This is one of a series of videos in the Reimagining Pre-Calculus project. Our goal in this series of videos is to give you quick foundational concepts for pre-calculus and apply that to a real-world application. And in this particular video, we have 4 objectives. You can see them on the board. We are looking to represent intervals on the number line using mathematical notation. We'll spend a moment to distinguish the concept of infinity from the concept of numbers. There's a subtle difference there. Thirdly, we'll look to understand the importance of reading the context for mathematical notation, especially when it comes to intervals without infinity. And then lastly, we'll use some algebra to solve linear inequalities. And once we have all of this put together, we'll have a foundation for working through later concepts in pre-calculus. This especially applies to the domain of a function, which is one of the key concepts in pre-calculus. And then by the end of all that, we'll be able to look at one application of this notation to linear regression. So let's get started with the number line. This is something you may remember from other math classes you've had. And to really give a good grounding for what's to come later in this video, we should go through a couple of the ways that you can think about the number line. So you can see a schematic over here on the right. It's just this one-dimensional line, goes in both directions. I like to think of it as an idealized ruler, so you're measuring every location precisely. You could also think of it as a one-dimensional continuum. So every number along the number line is marked here. The whole numbers are marked. You can imagine any number whatsoever in between them. So I've given a few. There's negative 2.5. That's on the number line. We have numbers like 1/2, numbers like square root of 2, and we even have numbers like pi floating around in between these whole numbers. And then for the purposes of the naming that we give to it later, we often use the word origin to refer to the 0 point. So imagining here the 0 point being the origin of one-dimensional continuum, we have all these whole numbers, lots of numbers in between, and it looks a bit like an x-axis. And from this x-axis, we often put a y-axis vertically. So for now, since we're looking at one dimension, we can think of that as an x, although different variables can be used and it means the same thing. So my proposal for a definition for our number line is that we take all the whole numbers, these are the ones marked on the right, we take everything in between, so any of these points that I've labeled in between those whole numbers, and then any numbers that go beyond. And this is why I've written on the left and on the right that it goes to infinity on the right, or minus infinity on the left. For our first example, let's look at this question. I've written it out in words. So we would like to know when 2 minus 5x is positive and less than 7. So the first thing to do in a problem like this is to take it out of the written word and put it into a written mathematics. So first of all, we're looking at 2 minus 5x. We want it to be positive. So in inequality form, let's write out the inequality below. We need 0 to be less than 2 minus 5x. So we're just saying 2 minus 5x. It's greater than 0. It's positive. And then we also have the condition that it's less than 7. So typically those get combined into one equation, an inequality. 0 is less than 2 minus 5x is less than 7. So what I'll ask you to do here is to take a moment and try it out, and then we'll move on to the next part. OK, welcome back. Now let's do the algebra for the solution. And in the end, we'll see how to write things with our interval notation. So given the inequality, one of the things you can usually do with an inequality is operate on it the same way you might do it with an equal sign. That's not always true, and I'll explain what's different about it. But if we just take that as our first step here, we can add or subtract any of these terms in the middle as long as we do it to all 3 parts. So what I'll do here is subtract 2 from everything. We'll do it over here on the right. So if I've got 2 being subtracted, I have negative 2 now, less than negative 5, x, less than 7 minus 2, which is 5. So we have our inequality. It's changed just a bit. We're still keeping it all together. The next step is to divide out by the negative 5. And we are just solving for x. So once x is isolated on its own in the middle, we're done with the problem. Now here's the part that's different from a regular equation. If I divide by negative 5, let me write it out with the negatives. So I have negative 2 over negative 5. I would want to say less than x. And then I also have 5 divided by negative 5. I'd like to have my inequalities that way. The trick is, I've divided by a negative. I can't leave these inequality symbols in the same direction. I have to switch them. This is the one thing that's really important to remember. So we switch our direction when we divide by a negative. And now we can simplify to get our final inequality. So the negatives on top and bottom on the left will cancel. So I'll have a 2 over a 5. 2/5 then will be greater than x. X will be greater on the other end, greater than negative 1. The 5s would cancel. The negative is all that's left. So the answer in inequality form is right here. 2/5 is greater than x, which is greater than negative 1. So there's our inequality solving process. We can mostly treat it like it's an equation with an equal sign, unless we either multiply or divide by a negative. In this case, we divided by a negative number, and we had to switch the direction. Now let's think about the interval notation. So if I write out my answer as an interval, the way the notation works is we take the smaller of the two numbers, so the lower bound, here it's negative 1. We list that first. We put in a comma. We take the upper bound of 2/5. And the idea here is we are representing all the numbers between them. X is stuck between negative 1 and 2/5. We've listed them in increasing order. And based on the inequality, we know that we're not allowed to have negative 1 itself. X has to be strictly greater than that. And we can't have 2/5 itself either. It has to be strictly less than that. And the way the notation works here is we put in parentheses to indicate that. So in this case, we have the interval from negative 1 to 2/5. So it's all the numbers in between, but it doesn't include either of those numbers on the endpoint. So let's do one last thing with this example before we move on. So I've written out here a visualization for the interval. You can see the answer we arrived at. It was the interval negative 1 to 2/5. And on the number line underneath, I've marked off the space from negative 2 to 2 on the number line. And since we're not including either of these intervals, the way we represent that on the number line is by having an open circle at that location. So negative 1 is circled. It's an endpoint, but it's not filled in because we're not including that point in the answer. And then the 2/5 is the same way. We have an open circle there. And then I've shaded in between those 2 points to indicate where the interval is. So if you're the sort of person who likes having a picture in your head as you're working through these, you can imagine sitting in this one-dimensional continuum, and we have our interval bounded between those two endpoints. One thing that's especially important with an interval like this is, since we have parentheses and since we have two numbers listed with a comma in between, it looks a lot like it's a point in two-dimensional space. So it looks like something like an x comma y, where we think of x as a horizontal and y as a vertical dimension. So if you're not watching the context, you might think at first that it's a two-dimensional point in space. But for intervals, it's really important to remember it's not two-dimensional, it's one-dimensional. So having this picture makes that extra clear. We have a region in one-dimensional space that's an interval. It's not the two-dimensional point in space. And unfortunately, they look like each other. The notation that got chosen here wasn't the best. So what you should do when you're reading through problems in this area is check the context. it should become clear by reading over the whole problem or the whole paragraph what kind of thing they're talking about. So if it's a two-dimensional description, you'll know it's a point in two-dimensional space. And if it's an interval, or if only x values are being referenced, or if it's an inequality problem like the one we've just done, then you'll know from that context that it's a one-dimensional interval instead. For our next example, we'll do a statement that's slightly different. It'll illustrate a couple of the different properties that we have for inequalities. I want you to take a moment and think about how you would start this problem and how the algebra would allow you to solve for x. So take some time to do that, and then we'll move on. Now, this is the first point in the video where we've had the concept of infinity in play, and it's one of those concepts that's hard to wrap your head around. So let's take a few moments to really think about what it means and how we use it in mathematics. Sometimes we can think of infinity as being an absence. And what I've been saying mathematically in this example is a lot like that. I've been saying that you can start at 4 and you can get as large as you like. You might say there's no upper bound for this interval. So we're not saying that there is an infinity, we're just saying there's not an upper bound. So you can think of infinity in this way as an absence of something. It's the absence of an upper bound. Another way to think about it is as a presence, as a thing instead of the lack of a thing. So you could think of infinity just abstractly as the quantity that goes beyond all finite quantities. So on the number line, it's the arrowhead at the end. You can think of it as the quantity beyond all finite quantities. So in pre-calculus, we tend to think of the first one, of infinity, as an absence. So just remember, for intervals, we're looking at infinity. We're not treating it as a number. We can't include it in the interval. We always have the open parenthesis. So that's the absence of an upper bound that we're indicating. If you look into calculus, a lot of the origin of calculus is the merging together of the two different ways of thinking. So if we think of a presence and an absence together, a lot of concepts that gave rise to calculus come into that together. So if you're thinking ahead to taking a calculus course, you will see both concepts. For now, we'll think of it as an absence. Now let's look at an application for intervals. What you're seeing on the screen here is the percentage of U.S. electrical power generated from wind sources, and this covers the years 2001 to 2018. Now, we do have the specific data available. You can see starting with year 17, which is 2018, at 6.704%. That's the value on the far right of the graph. And then going all the way back to the year 2001, which we take to be the year 0 in our model. And then at that point, it was 0.181%. Now, in this case, I've chosen to use a line equation to model it. You can see that also at the bottom. So if f of x is 0.4x minus 0.6, we're looking at that line in red on the graph. And we can see that's a rough approximation of the growth in wind power over these years. So one thing we might like to know is what years had a percentage of wind power between 3 and 5%. If we're looking at the data itself, that's pretty easy. We can look at year 10 being about 3%, and then up to year 14 being slightly less than 5%. So we get a range to expect there. But there are cases where we don't have access to the data right at the moment, so we would like to know how those might be computed from the line equation, from the model, instead of from the data table. And that's pretty easy to do, and I'll do it over here on the left side of the screen. So we can take the percentage and set that equal to 3 and 5 to get what we need. So if I'm down here for my function, I can take my percentage 3 equal to 0.4x minus 0.6. And on the graph, this gives us a line. It doesn't really matter that it's a line so much as the fact that we can see that it goes through a horizontal coordinate of 9. When time is 9, we're in year 9, we should expect to be at about 3%. And then if I make the change over to a 5% scenario, we see the line moves over to 14. So the answer here then is that between years 9 and 14, so 9 to 14, the percentage is between 3% and 5%. Now, we're measuring years from 2001. So if you think for a moment, year 9 is 9 years after 2001. So we could say 2010 to 2015 in that answer. Now let's ask a slightly different question. I'd like to know percentages corresponding to the years 2012 through 2018. And instead of knowing the percentage and wanting the years, well, now we know the years and we want the percent. So we're interested in 0.4, and we're taking x to be the year 2012. That's going to be 11, year 11, 11 years after 2001, minus 0.6. So we get a 3.8. If I go with the other year, which was 2018, I'm looking at year 17. So naturally, if I change 11 to 17, I get the other percentage of 6.2. So from this, then, we know that from the years 2012 to 2018, that percentage is between 3.8% and 6.2%. The answers looked much the same. We just arrived at our answer in a reverse process. Now, what I'd like to do before we finish is express both of those in terms of intervals. So if we go back up to our top example, we know that the percentage is between 3 and 5, and that was our starting point. We now have years being 9 to 14. So since we're including our endpoints, we take a square bracket, 9 to 14. In the other version, we knew what the years were. We wanted the percentage, so our answer would be an interval of percent values, and in this case, 3.8 up to 6.2. In both cases, we list these values in increasing order. We're taking square brackets here under the assumption that you would include the year 2010, or you would include the percentage 3.8, and that might vary depending on what type of data you're looking at. But in this case, we can see that modeling data with a line and making estimates from that give us intervals as answers. So let's recap everything from this video. There are a number of different things we did. One of the first things is to note that intervals on a number line, or we think of it as an x-axis or a one-dimensional continuum, are represented with pairs of numbers. So we list two numbers to indicate the interval. If there's parentheses on either endpoint, that means that we're excluding it. It's not part of the interval. And then if there are square brackets, we're including it. It is part of the interval. Then also, if you see infinity or negative infinity, those always come with parentheses. We don't think of infinity as a value like a number. It's an unbounded interval. So always include parentheses in that case. We also saw that parentheses can make an interval look like it's a point in two-dimensional space. So you want to be careful to read context so you're interpreting it as the right thing, whether it's a point in space or an interval. And then when we're working the inequalities, when we're doing the algebra to solve it, if we have to divide or multiply by a negative quantity, that will require us to change the direction of the inequality symbol. So a less than would become a greater than, and vice versa. And then lastly, as we solve our inequalities, the solutions to those inequalities are intervals. They're bounded or unbounded. We have square or open parentheses, but those can always be represented in interval notation. To conclude, as you think ahead to other topics, just remember that interval notation shows up in lots of different places, in particular when looking for the domain of a function, looking for intervals of increase or decrease, and then also when using test points. And all of those will come up as we think about functions in pre-calculus. Thanks for watching.